everyone. My name is Jean Pakowski, and my tech talk is going to focus on haptic feedback, and specifically its application to surgical training. Today's presentation is going to focus on the following areas. We'll begin with what exactly is haptic feedback, and then move into why it is important for surgeons in particular. We'll go over various definitions to help define this current status, and then delve into the current state of the art and how the technology is being used today in both surgical training and in the real world. We'll then move on to discuss some of the limitations in the way that haptic feedback is delivered and used currently, and then lastly, we'll focus on a few future directions that may be considered in future research efforts. So what exactly is haptic feedback? Haptics refers to the interaction between a tactile stimulus provided by the environment and a combination of cutaneous and kinesthetic sensors in tendons, ligaments, joints, and muscles. It may also be considered active touch. A haptic device is a mechanical input-output device that enables the user to interact with virtual environments by adding a sense of touch. One of the earliest uses of this technology was in the aviation industry. External forces that were not felt at the controls could be recreated with vibration mechanisms in the cockpit to alert pilots to the presence of dangerous flight conditions. Haptic devices used in simulation have mechanical handlers that can move with several degrees of freedom, typically between 3 and 6. 3 degrees of freedom can be thought of as the traditional X, Y, and Z axes, whereas rotational or twisting forces can be achieved with the addition of 3 more, leading to 6 total degrees of freedom. Devices with force feedback allow the user to distinguish between different materials. For example, the feel of hard bone versus soft tissue, or diseased versus healthy tissue, with 1 or more degrees of freedom. 1 degree of force feedback would allow the user to feel the force differences in only one plane, whereas a more complex device with 3 degrees of force feedback would be needed to feel the force feedback in all 3 planes of motion. Devices with 6 degrees of force feedback, as would be necessary to feel twisting or rotational forces, are rarely used and difficult to obtain. Why are haptics so important to surgical trainees and to surgeons in general? For several reasons. With increased emphasis on patient safety, surgical educators are looking for ways to improve trainees' motor skills before they ever encounter a live patient. Simulation is an obvious choice, but conventional simulators do a poor job of replicating the feel of live tissue and its interaction with surgical instrumentation. Surgery requires complex motor tasks, and surgeons rely on a combination of visual and haptic data in order to perform them correctly. Especially in minimally invasive surgery, such as laparoscopy, endoscopy, and arthroscopy, the tools used to perform a surgery will attenuate haptic feedback and force the surgeon to rely more heavily on visual cues and their own personal experience. This demands a higher cognitive load and may decrease the surgeon's ability to perform the procedure quickly and with optimum results. There are several terms that relate to haptics that are helpful to understand when looking into this technology. Resolution, as it relates to haptic feedback, is the amount of feedback per unit distance. A higher resolution provides greater detail of textures, allowing the user to distinguish between different materials or tissue types. There are 2 main variations in how feedback is delivered to the user. In impedance control, when the user moves the device sends the movement data to the computer, which then generates the feedback delivered to the user through the instrument. In admittance control, the user exerts a force on the device, which reacts by displacing a proportional distance to the force delivered. This provides the user with more freedom in terms of mechanical design and produces movements with greater force and stiffness. However, it is more complex to design than impedance control and is not commonly used in training modules. Rendering refers to the ability of the device to enable the user to feel, touch, and manipulate virtual objects through a haptic interface. In geometry-based rendering, the user deforms an object based on geometric manipulation. For example, the user may manipulate the position of vertices of a shape to modify it. And this form of rendering is fast and easy to implement, but it doesn't necessarily recreate the actual deformation of an object that would be expected in real life. Physics-based rendering adds physics simulation to the modification of geometry by modeling physical laws involved in the movement of the object and the dynamics of the interaction. This is much more realistic in terms of how actual objects move and deform, but does require more complex software and is consequently more expensive. Now let's delve into the current state of the art. Haptic feedback technology is currently used in many medical specialties for both training applications as well as real-world surgeries. These include neurosurgery, general surgery, otolaryngology or ENT, urology, orthopedics, dental surgery, and basic procedural skill training such as stitching and palpation. A few of the more common devices available are listed here. The Novant Falcon is a desktop haptic device with 3 degrees of freedom that can be used for simulation and gaming interfaces. It is relatively inexpensive at about $200, but lacks degrees of force feedback. The Geomagic Touch, formerly the Phantom Omni, is a lightweight device with 6 degrees of freedom and 3 degrees of force feedback. Due to the increased complexity, it tends to be more expensive than the Falcon device at approximately $2,200 as of 2015. Magnetic levitation haptic devices are a relatively new technology involving the use of strong magnetic fields and a movable floater that floats between the magnets and is optically tracked. This may increase the ease of motion as the device is not rigidly tethered to a base as are the conventional haptic devices, while still being able to provide force feedback. Multiple gaming haptic devices also exist on the market, which are currently more affordable and readily available. However, they tend to rely more heavily on vibratory feedback, which does not adequately recreate surgical haptics and can be distracting enough to adversely affect surgical performance. A few examples of medical simulators with embedded haptic technology are demonstrated here. The ForgeFX NeuroTouch Cranio, shown at the top left, is a high-fidelity simulator designed to teach neurosurgical residents how to properly debulk tumors, perform microdissection, and achieve surgical hemostasis. It has been modified to allow for endoscopic decompression of the third ventricle for cases of hydrocephalus. The Arthromentor by Symbionics at the top right allows for high-fidelity arthroscopic surgical training for knees, hips, and shoulders. Both of these devices use conventional haptic devices with 3 degrees of freedom. The Vertimed Arthro S simulator, shown at the bottom, also allows for advanced arthroscopic surgical training, but utilizes magnetic haptics. This allows the trainee to have greater freedom of motion with the camera and instruments while still receiving force feedback. There are several limitations as it relates to the use of haptic feedback technology in medical simulation. First, the addition of these haptic devices to medical simulators can add significant cost. While simpler, low-fidelity task trainers can provide adequate training without haptics, more complex surgical modules require at least 2 haptic devices to provide realistic sensation of both the camera and the instrument. In order to distinguish between tissue types or disease versus healthy tissue, realistic laparoscopic, endoscopic, and arthroscopic trainers require at a minimum 3 degrees of force feedback. The haptic devices with 6 degrees of freedom and 3 degrees of force feedback are significantly more expensive than those with fewer degrees of freedom and 1 or no degrees of force feedback. In some cases, haptic devices may become a distraction for the trainee, especially if there is significant friction or vibration within the device. This may also lead to fatigue as the trainee tries to balance task completion with the need to suppress or ignore the odd haptic sensations. Multiple studies have evaluated the use of haptics in medical training. While overall the literature is contradictory, patterns do emerge. In simple tasks such as suture management and knot tying, the addition of haptics to the simulators does not appear to improve trainees' performance. This may be due to the fact that these tasks do not require significant haptic feedback to perform well, as they rely more heavily on visual cues. Additionally, these tasks are typically learned by very junior trainees or students who may be so focused on the task at hand that the haptics provide an unnecessary distraction. In a study evaluating haptics in virtual reality simulators used by more experienced surgeons, an initial survey demonstrated that most surgeons felt that haptics would be helpful and were desired for laparoscopic training, but they were then asked to complete laparoscopic tasks with both haptic and non-haptic tool handles. They were blinded to the type of handle being used. In the end, the surgeons preferred the handles without haptics, as there was too much friction in the haptic handles that was felt to be unrealistic. However, these were more experienced surgeons that were used to not having haptics, so the findings may indicate that these surgeons had learned with time to use almost exclusively visual cues and would need to acclimate to the haptics. As it relates to more complex procedures with inexperienced surgeons, such as a laparoscopic gallbladder excision, the addition of haptics has demonstrated improvement in early performance with decreased time to the training plateau and improved performance metrics compared to similar level trainees without the haptics. In the end, it appears that haptics may be useful for more complex training modules with less experienced surgeons early in their training. For simpler procedures and more experienced surgeons, the cost of haptic feedback may not be justified. As medical simulation becomes more prevalent in surgical education, the question of haptics will continue to be important. Future research efforts should investigate new technology for haptic feedback, such as comparing magnetic to conventional, and other technologies that may develop to increase freedom of motion and decrease cost. The research to date has evaluated the acquisition of surgical skill with haptic simulators, but has not investigated skill maintenance, transfer of virtual reality surgical skills to the operating room, and whether or not simulation with or without haptics can decrease skill decay. The exact areas in which haptic feedback does significantly improve performance continues to be studied and will hopefully clarify when the cost is justified. Here are a few starting references that may be helpful for anyone interested in looking more deeply into haptic feedback technology. This concludes my presentation on haptic feedback and its application to surgical training. Thank you for your attention.